Hello, I am Marcos Jimenez, and I'm here to present the second lesson of this third section, the 12th of the course, entitled Intensity Associated with a Wave, which we are going to develop according to this 4-point index, and we start with the first one. The fundamental hypothesis for this whole lesson is not a certain hypothesis, but what we are going to assume is that it is fulfilled, that the wave propagates without loss of energy. That is, if we have a source that emits, for example, at 16 joules, then we continue to have 16 through the front. That comes next, the next, the next, the next, that there are no losses. During the path, which can be distributed among more or less wide areas, but there is no loss of energy, that will be part of what we will mention in later lessons. Well, under this hypothesis, it turns out that what happens with the energy depends, to begin with, most importantly, on the number of dimensions in which it propagates, and secondly, it depends on this number of dimensions, what is the shape of the fronts. We will speak, according to this table, in one-dimensional, two-dimensional, and three-dimensional waves. As a general rule, whenever we have a wave propagating in a number of dimensions, the fronts are of the same dimension minus 1. For example, one-dimensional waves, such as, for example, traveling waves in a series of springs, dimension 1, 1 minus 1, 0. The zero-dimensional fronts are points. This would be a front, this point would be another front, this point would be another front. In the case of two-dimensional waves, for example, waves on the surface of the sea, we would have that waves if they propagate in dimension 2. 2 minus 1, 1. The fronts are lines. For example, straight lines. The typical one that we see when the waves arrive at the beach. Circular, circumferences. As when we throw a stone in a pond or any other shapes. Three-dimensional waves, which travel throughout space in 3 dimensions. Light, sound, earthquakes. In that case, 3. Dimension minus 1. 2. The fronts are surfaces. They can be planes, they can be spheres. They can be cylinders, or other shapes in general. Let's make an additional simplifying assumption. Let's assume that in addition to the fact that there are no energy losses, the power supplied is at a constant rate, which does not depend on time. If it did, everything we are going to see would be functions of time. For simplicity, we would assume that time has no influence, that there is no variation with it. First question, what happens in a linear surface wave with straight fronts? How is the energy distributed as it travels? Well, let's look at it with this virtual laboratory, with a kind of economic simulation. We have a source, which is the line on the left, where there are 16 joules. That is, they are coins. Each coin, because it represents 1 joule, the currency of the country of the energy, that are going to travel, being emitted to the right. Those 16 joules, as we see, are going to arrive at the line, at that front, where there is another coin. There are 8 jacks waiting, and therefore, they play, as we can see in the animation, at 2 joules for each jack. Let's assume that each jack has a head of 1 meter, and that therefore we have 2 joules for each meter. We are not simulating with coins for each head. In reality, it would be joules per meter. Well, the most important case is that we can see that the propagation continues, that the coin, the energy, arrives from the pulse to the next front. And it is still 2 joules per jack. It has not changed at all. So, first important detail, the rate of energy through each front is the same. Of course, that's the assumption we're making, that there are no losses. But what is new? The rate of energy going through each front per unit length is also the same. Well, this second is not a general truth, as we are going to see here. What happens in a circular surface wave of circular fronts, like the one that comes out when we throw a stone into a pond? In this case, we're going to emit 24 joules from the center. That's the source. A point source that will emit in all directions equally, and they're going to make the trip. Here we have the 24 joules. Moving to the first front, where there are 12 jakes waiting, so it takes 2 joules per jack, 2 joules per meter, accordingly. However, we can see that the next front, with twice the radius, also has twice the length. It's the formula for the circumference, 2πr. So, there I have twice as many meters, twice as many joules, and since they are still the same number of coins, we have 1 joule per jake, 1 joule per meter. We have a distributed energy, the same, there has been no loss of energy, but it has been distributed over a larger area. The same effect we are going to see now, instead of with a pulse, with a continuous emission, like this one here. It is exactly the same, just that the emission is continuous. Now, for example, waves are being emitted every quarter of a second, so we are having 4 emissions per second, which would be 4 times 12, 48 joules every second, 48 watts consequently. Conclusion, therefore, that we have here. The rate of energy through each front is effectively the same in the starting hypothesis, but we are already going to the second conclusion above. The rate of energy through each front per unit length is not constant. It is inversely proportional to the distance, and this is another particular case. There are more possibilities. This brings us to the following definitions: intensity and attenuation. What is intensity? Definition: it is the rate of energy, joules per second, watts accordingly, passing through each front element. In the case of one-dimensional waves, per point. In the case of two-dimensional, per unit length. In the case of three-dimensional, for each unit of surface area of the corresponding front. Obviously, the unit also depends. In the first case, the intensity is measured in watts itself. In the second, in watts per meter. In the third, in watts per square meter. The next relevant definition. What is attenuation? Attenuation is the decrease in the intensity of a wave as the energy is spread over wider and wider fronts. Not to be confused with loss of intensity, because there is loss of energy. This is not the case. There is no loss of energy. We are simply having that the energy is distributed between wider areas and, for example, touch less. That is the concept of attenuation. Let's remember anyway, because it is relevant, that energy is proportional to the square of the amplitude. So the same thing happens to intensity. If the amplitude doubles, the energy quadruples and the intensity quadruples. Well, let's now look at the following possibilities. First case, one-dimensional waves. So we have that the intensity is measured in watts because it is per point. In this case, we can see as an example the series of springs that I've already been mentioning as an example previously. Here we have a series of springs. We are providing energy continuously, a constant power to the first bead, and that power is being emitted. If, for example, it were 20 watts, well, here we have 20 watts, here 20 watts. Any front has the same intensity. Therefore, the intensity does not depend on the distance. The intensity is equal to the power at any time because, I insist, we are suffering no losses. What happens in the case of two-dimensional waves? It depends on the type of front. Let's say we have linear fronts. In that case, what would happen? We would have an emission from a line, which would be propagating to one side, and all fronts would have the same length as the source. Therefore, the intensity would be power divided by length, and would not affect the distance. This would be the case of what we saw with Jake when he was handing out coins to the right, and what we can see here simulating a wave. We add intensity, it travels to the right, and when it is stabilized and does not depend on time, we can see that any point has the same amplitude, therefore they have the same intensity. And the intensity does not depend on distance. It depends on whether it has to be distributed over a greater or lesser length. And what happens in the case of circular waves? In the case of throwing a stone into a pond, well, each front measures 2 pi by the distance at which we are. So you have to make that quotient. Power between the length of the corresponding front. That means that at twice the distance we have half the intensity, as we would see in this laboratory that I am going to show now. It would be, as I say, the simulation of throwing a stone into a pond. We could see how the amplitude of the waves decreases as we move away. We can think that it does not decrease so fast. Recall that if the intensity decreases with distance, the amplitude decreases with the square root of the distance, that of the relationships between intensities and amplitudes. What about three-dimensional waves? Let's see the examples with light, but the same does not apply to sounds, earthquakes, and so on. If we have a plane wave, that is, we have a plane-shaped source that travels a distance, all fronts have the same size, so the intensity is P divided by a constant S. Therefore, the intensity is constant, and I insist once again, if there are no losses. It would be the case, for example, of opening a window. And once it stabilizes, then we would have that the intensity does not change from one point to another. We have exactly the same. All points are equally illuminated. On the other hand, if the surfaces are spherical and we have that is emitted from a point, for example in the case of light, a light bulb, in the case of sound, a point source, a siren to the mouth of a person, it turns out that it depends on the front of the squared radius, 4 feet squared, at twice the distance, we will have a surface area 4 times larger, and therefore an intensity 4 times lower. This would be the example we are going to see here, which is, as I say, that of a lamp emitting light. Even if there are no losses in the medium, it turns out that the light is more intense near than far, because it has to be distributed over a larger area, although there is no loss of energy, and that should also be considered, but not in this lesson. In the case of cylindrical waves, as is the case of a fluorescent light tube, for example, emitting waves in the shape of a cylinder, we can see that the fronts would measure 2 pi r by the L. Therefore, they decrease with distance, not with their square, so as we can see each type of propagation dimension and the shape of the fronts is relevant. But more generally, what if there is no geometric shape as above? For example, a swell that is arriving here at this protective wave breakwater, and we have an interval through which it can enter, and we have done it right on top of a submarine cannon. Why do I say that? Because it would be that the canyon is upwards and it's shallower to the side. The consequence would be that since the waves run faster the deeper the sea is, and as it gets shallower they are slower, it would turn out that they would run more along the canyon than sideways. The result is what we see here, or what we are going to see even better with a virtual laboratory. It would turn out that, as we are going to see now, the central part, the particles, the joules, the central coins, run faster than the lateral ones. That's why it takes that shape of the front that you see there, or that you see here. Relevant to these questions is that the rays, the red line, are perpendicular to the fronts and have the shape that you see there. And as a consequence, you will notice that here there is a higher energy density. There are more coins per meter than here, or than on the opposite side. That is to say, the swell is more intense in front of the mouth than on the sides. So, an interesting property. We were giving the impression that the same rate of energy across each front meant that it is evenly distributed. This is not true. It happens with the simple geometric shapes that we've been looking at so far, but it's by no means a universal truth. What happens is that we are not going to contemplate this case, because it is rather more complex. We will stay with the others, but I think it is interesting to be clear that it is not a universal truth. Therefore, in general, there can be a change of energy, of intensity, from some points to others. That means that we would have to work with derivatives. I put them here for illustrative purposes so that we have the idea that this is more complex than it seems, but it is not part of this subject. I just don't want you to get any misconceptions. For the same reason, if what I want to see is how a receiver captures energy from a wave, for example, what a parabolic antenna does capturing an electromagnetic wave, then we must proceed to an integration of the intensity of each point, because it varies from one to another. But here again, we are not going to keep in this lesson that topic. Let's assume that the intensity is the same. For example, that we have in this case. A wave, for example, waves propagating in straight fronts, so that the intensity is the same at all points, it does not change. Therefore, the integral is simpler. It is simply multiplying y by area, but what area? Or in this case, what length? Since fronts are length. Let's say these are waves and we are going to intercept them with a device that wants to capture energy and has a fancy shape like this. Is the length of the device relevant? Well, no, because it turns out that what it really interrupts is the lines that we are going to cut. What matters is how long that distance is. That distance, because that's the length of the front that it intercepts, before or after. Well, then it means that the power captured by that device is the constant intensity to avoid the integral by the length in the normal direction perpendicular to the rays. Not the real length, but the length of the projection on the perpendicular direction, on the orientation of the fronts. I am not going to make a drawing here, we will do it later, but the same thing happens with the three-dimensional ones. We will have to multiply intensity not by the surface to which we are applying all this, but by its normal component, as is going to happen here. What happens when the sun is below and we have to heat that piece of ground called S under Jake's feet? The rays come in quite slanted, quite oblique with respect to the vertical. Well, it turns out that, as we can see, S is obviously not normal to the rays. The surface normal to the rays is this, and it's the one that I care about to see how much it's heated, because only the energy passing through the blue rectangle is reaching the surface S that I'm interested in, and that Sn is quite small. When the sun is higher, the direction of the rays is different. And now we can see that the surface normal is much wider. Therefore, if the surface normal is wider, obvious consequence, the power is also higher. Therefore, apart from the fact that we are assuming that the intensity is constant, which is not true, it is hotter at noon for effects that we will see later than at sunrise or sunset. The result is that it is hotter. That is to say, it warms up more at noon than at dawn or at sunset. And in summer, since the sun reaches higher than in winter at noon, it also warms up more. I put here already the summary of the lesson, with which I am all this for finished. Thank you very much for your attention.